Okay, so we'll start our session with a question from the study guide 9. Self-test 1, question 4. So the question reads the following. A tuning fork is set up near the end of an air-filled tube of variable length as shown. So this is the tube. With variable length. This is variable. We have a fork here. So as the length of the air column is changed, we hear resonances as we match the length of the wavelength to the harmonics. By changing the tube length by 10 centimeters, we go from one harmonic to the next for the sound wave. A, what is the wavelength in air of this sound? B, what is the frequency of the tuning fork? C, would closing the right hand end of the tube change the measurement of 10 centimeters? So let's start first with the A. So since we have an open end, in this case, my length is given by this equation, lambda over 2. So my fundamental wavelength, my fundamental frequency will be of lambda over 2, and then it will be an n number of lambda over 2 for the harmonics, such that n goes from 1, 2, 3 as an integer number. So in this case, if I am to take the general two harmonics, let's assume that the first one is Ln, that equals to n lambda over 2. And the next one is L, which is n plus 1, equals to n plus 1 lambda over 2. So if I take now the difference between those two, then L n plus 1 minus L n, which equals to n plus 1 lambda over 2 minus n lambda over 2. I know that this one is 10 centimeters, and this one is, I'll distribute n lambda over 2 plus lambda over 2 minus n lambda over 2. So n minus n lambda over 2 minus n lambda over 2 will cancel, and we'll end up with lambda over 2 equals to 0.1 meter, and lambda is 0.2 meter. So this is the wavelength for the sound generated by the fork. B, what is the frequency of the tuning fork? We know that V equals to F lambda, and here we will take the speed of the sound in the air as 340, and in this case F is V over lambda, and F is 340 meter per second divided by 0.2, and the frequency is 1700 hertz. C, would closing the right hand end of the tube change? So this is my tube. If I close the right hand here, and this one is still as a variable, would that change the differences between my resonances to be 10 centimeters? Let's see. So in this case now, the fundamental frequency here will be n lambda over 4 wavelength, lambda over 4. So in this case, if I take Ln as n lambda over 4, then the next resonance will happen at n plus 2, which basically an odd number. So if we were starting with 1, then the next one would be 3, after 5, the one after 7, and so on. So now this one becomes n plus 2, starting from n equals to 1, lambda over 4. Now if I take the difference here, Ln plus 2 minus Ln, this is n plus 2 lambda over 4 minus n lambda over 4, n lambda over 4 plus 2 lambda over 4 minus n lambda over 4. Then this will cancel, and this will still give me minus Ln will still give me lambda over 2, which is the same as the open. So the answer is no. There's no change. I will be getting the resonance frequencies at the same difference in the length. Any question about this problem? Okay, so let's move on to the next question. Next question is from the textbook 1494. Question 1494. This question reads the following. The maximum intensity levels of a trumpet, trombone, and bass drum, each at a distance of 3 meters, are 94 dB, 107 dB, and 113 dB, respectively. So here I have beta 1 equals to 94 dB, 94 dB. This is for trumpet at 3 meters. Beta 2 is 107 dB. This is for trombone at 3 meters. And then beta 3 is 113 dB. At 3 meters. What is the intensity level of 3 such trumpets playing simultaneously at the same distance of 3 meters? This is A. B. What is the intensity level of the 3 different instruments played simultaneously again at 3 meters? So we have here the distance is not going to change. I need to find the new intensity if I have 3 trumpets now at the same distance. So in this case, I will write that at beta 1 prime, that equals to 10 natural logarithm of I1 over I naught. However, I have 3 trumpets, that's why I will multiply by 3. So I have 3 times the intensity because I have 3 trumpets that are at the same location. Now this one is beta 1 prime equals to 10 log I1 over I0 plus 10 log 3. Now this one is 74 94 plus 4.77, and then beta 1 prime as 98.77 dB. This is for A. Now for B, I need to calculate now the intensity for all of them. If I want to calculate the intensity for all of them, then I have to first find the intensity for each. Well, basically here I know beta 1 equals to 10 logarithm I1 over I0, and then beta 1 is 94 10 log I1 over I0, and then if I divide by 10, then I get 9. Let me change and start with log I1 over I0. Then divide by 10, this becomes 9.4. Now let me show you here how did we move to the next step. However, by this is intermediate step here, I1 over I0. This 9.4, if I take this one as the result of the logarithm of 10 to the power 9.4, then by removing the logarithm, I get I1 over I0 equals to 10 to the power 9.4. So this is how we got the 10 to the power minus 4. Then I1 is I0 times 10 to the power 9.4. I1 is 1 to the power minus 12, which is the threshold, times 10 to the power 4. I1 equals to 0.0025 watts per meter square. So this is I1. If I want to get I2, it would be the same. Then I know I2 over I0 equals to 10 to the power 10.7, the same thing, 10.7, and then I1 would be, sorry, I2 would be 0.05 watts per meter squared. Same thing here, I3 over I0 as 10 to the power 11.3, right, it's 113. Then I2 as 0.1995 watts per meter squared. So now those are the 3 intensities in watts per meter squared. Then if I want to calculate now the beta total, will be 10 logarithm of, if you add those ones, it will be, let me put here I tot equals to 0.252 watts per meter squared. Then here I tot divided by I naught. Then beta tot equals 10 logarithm of 0.252 divided by 1 to the power minus 12, and then beta tot is 114 dB. Problem 114. Problem 114 reads the following. Some of the terminology associated with stereo equipment is found in each part of this question. A recording system has a signal-to-noise ratio of 58 dB. Calculate the ratio of the intensity of the signal to intensity of the background noise. So we need to find the ratio between those two intensities, the signal and the noise. If I know that the signal to noise ratio in dB is 58 dB, so I know S over N in dB equals to 58, which means if I want to calculate S signal to noise ratio, I know that 10 logarithm of S over N equals to, so let me say this, signal to noise dB equals 10 to the logarithm S over N, or 10 logarithm S over N equals to 58 dB, or S over N as 10 to the power 5.8, or S over N, the ratio between the signal to noise as 6.31, 10 to the power 5 times. So this is A. B, a stereo speaker has a flat response of 4 dB, which means that any two signals of equal power sent to the speaker result in sound intensity levels coming from the speaker that differ by 4 dB or less. Determine the maximum variation as a ratio of sound intensities produced by this speaker. So here we have I2 over I1. So let me say this in dB plus 10 logarithm I2 over I1, or I2 over I1 equals to 10 to the power 0.4, which means I2 over I1 equals to 2.512 times 115. The wavelength of the waves in an ultrasonic cleaning bath correspond closely to the particles to be loosened and washed away. If these particles are 3 multiplied 10 to the power minus 2 millimeter in diameter, then what frequency in megahertz should be used in a bath containing alcohol, in which the speed of sound in alcohol is about 1.2 to the power 3 meter per second? So if you have so let's assume that the size of those particles, so the diameter of those particles, is 3 10 to the power minus 2 millimeter. And we have here bath of alcohol. Those are immersed in alcohol, or IPA. So we will pick the wavelength to be in the same range of the diameter of those particles. So if those particles are in the range of 3 10 to the power minus 2, around 30 micrometers, then my lambda should be in that range. So my lambda here, I will write it in meter, will be 3 times 10 to the power minus 5 meter. Now, if I know that the speed of those sounds in alcohol as V equals to 1.2 10 to the power 3 meters per second, and I need to find the frequency, I know that V equals to F lambda, and F equals to V divided by lambda. Then the frequency F as 1.2 to the power 3 divided by lambda, which is 3 10 to the power minus 5. And the answer to this is F equals to megahertz, X equals to 40 megahertz. One 18. In this problem, we have a mountain climber cannot stretch far enough to see how far a drop over a ledge is. So here, to estimate the drop, she tosses a small stone horizontally over the ledge and listens for the sound of the stone hitting somewhere below. The total time between the toss and the return sound is 8 seconds. The air temperature is 20, so T is 20 degrees. The time is 8 seconds. How high is that drop? Okay, so here, if if we assume that our coordinates are here, x and y, this way, then tossing the stone horizontally this way means that vertically the speed was 0. So if I am to look at this, this is going to do like this. So right here, v naught y is 0. So this is very important. And this is Vy that we don't know. Now, the time the stone takes to reach the bottom is T1. The time the sound takes to reach up is T2. So here I know that T1 plus T2 equals to 8 seconds. So it is, here there is a hint says consider both kinematics and sound. So the first time is due to the kinematics, T1, and the second T is using the sound. So let's start first with the kinematics. I have here this stone starting from rest, vertically going all the way down. I know that y minus y naught equals to v naught y t plus half ay t squared. However, since we're starting from the rest, the v naught y is 0, then this is 0. And y here is 0, then I have minus y naught equals to half. The acceleration is in this direction. Acceleration is pointing downward, which means it's negative, minus 9.8 t squared, and this y naught equals to 4.9 t squared, where y naught is this distance. This is y naught. Now, from the sound, I know that d equals to v times t, where d is the distance, v is the speed of the sound in the medium that I'm using, and time is the time. Now, the sound is going from the bottom up, which means my d here is y naught. So here, d is y naught. V is the speed of the sound in air, which is default 340 times T2. So here I have T1. This is my now T1. This is the T1, which is to the kinematics, right? So you can continue and put here if you want T1, T1. And now this one is T2. Now by equating those two equations, so if I call this one 1 and this one is 2, 1 equals 2, then I have 4.9 T1 squared equals to 300. Now, okay, let me back off here. I have the temperature here. If I am to consider the temperature, then I have I don't use the 340. I have to use a more precise number. So let me show you here. There's an equation that we can use. And by the way, we're flexible in that sense. If I am to bring you this question in the exam, then I'll tell you what type of sound speed and air you should be using. Here I said 340, but if I want to be precise, I will use this equation, which basically a temperature dependent equation. So this is V equals to 331 plus 0.606 T, where T is the temperature in degrees. So if I put now my T here as 20 degrees, which is what he gave me here, then V is not going to be 340. It will be precisely 343.1 meter per second. So this is the accurate speed of the sound in the air at a temperature of 20 degrees. If I did not mention the temperature for you, and it did not include this equation, which basically you don't have it in the formula sheet, then you go ahead and use the 340. But here, let's use the 343.1. So here we're going to put 3.1 just to be precise. Now, if I am to equate those two equations, then here I have 3.1 T2. Then moving T2 to the other side, then I have 4.9 T1 squared minus 343.1 T2 equals to 0. Now, from this equation, if I write this equation as T2 equals to 8 minus T1, and I call this one, let's say, 3, then this one call it 4, then I can say 3, substituting 3 and 4 will give me 4.9 T1 squared minus 3.1, 8 minus T1 equals to 0. Rearranging this equation, I get 4.9 T1 squared 3, 4, 3.1 T1 minus 2744 equals to 0. Then, solving this equation, I have T1 equals to minus B 343.1 plus minus B squared 343.1 minus 4 AC minus 2744 divided by 9.8 2A, then T1 is going to be 7.24 seconds. Now I got T1. I can substitute T2 equals to 8 minus 7.24 T2 equals 2.76. See the difference between the speed, between the kinematics and the sound. Now, after I got T2, I can calculate equals to 343.1 times 0.76. And the distance is 260.76 meters.